You know, I want you to imagine a scenario for a second. Just picture this. You are sitting in a hospital room, right? Visiting a friend.
Okay, setting the scene. I like it.
Yeah, so the patient in the bed next to them is sitting completely upright. I mean, they are happily eating a Tunky sandwich, filling out a crossword puzzle, maybe even humming a little tune to themselves.
Sounds like they're doing great.
Right, they look perfectly healthy. But the digital heart monitor sitting right next to their bed, it is absolutely screaming.
Oh, wow.
Yeah, mechanical alarms are blaring, the little LED lights are flashing this terrifying, strobing red, and the screen is just showing a flatlining 0. It's a dead flat line.
That's a wild disconnect.
Exactly. So what do you trust in that exact moment? Do you trust the highly expensive digital screen that's screaming a medical catastrophe is happening right now? Or do you trust your own two eyes showing you a perfectly fine, functioning, sandwich-eating reality?
I mean, it is the ultimate test of cognitive dissonance, really. Because in our modern era, our immediate, deeply ingrained instinct is to instantly defer to the screen.
Oh, 100%. We always trust the screen.
Right. We have been conditioned to think, well, the machine has complex sensors. The machine was calibrated in some high-tech factory. The machine sees invisible data, so it simply must know something I don't.
Yeah, we almost willingly dismiss our own physical observations.
Exactly. We just assume the digital interpretation of reality is somehow, I don't know, more accurate than reality itself. But as we see so often in technology, the machine is frequently, and I mean wildly, wrong.
I see a massive disconnect here between the screen and the physical desk. Okay, let's unpack this. Because before we can accuse the software of lying, we need to talk about exactly what we are plunging into today.
We really do.
Welcome to the deep dive. And specifically, I want to welcome you, the listener, to what today's incredibly detailed source material dubs the Solder, Silicon, and Voltmeter Lab.
I love that title. It's so visceral.
Right. Today, we are taking you right to the physical test bench. Our mission is to dissect a highly specific, utterly fascinating technical case study that explores what the PC building community calls the 3.3V myth.
The infamous 3.3V myth.
Yes, we are going to figure out if your computer is actually dying or if it's just, throwing a digital temper tantrum.
It is a phenomenal piece of investigative hardware engineering, I have to say. What the source material provides is a deep, truly methodical comparison.
It's super detailed.
It really is. It pits the terrifying red readouts of incredibly popular PC monitoring software against raw, undeniable physical hardware tools, like actual voltmeters.
And the goal here is to uncover the actual truth.
Right.
About hardware degradation, system stability, and here's the big one, a concept that makes a lot of tech executives very uncomfortable.
Oh, planned obsolescence.
Okay, planned obsolescence.
Yeah.
Because if you are listening to this, I can almost guarantee you've been in this exact situation.
I know I have.
Same. You've got your PC running. Maybe you spent $1,000 on it, maybe $3,000. You treat it like a newborn baby.
That's right.
You're doing some heavy 4K gaming or maybe rendering out a massive video project, and you decide to open up your monitoring software just to check on things.
Just a quick little check.
Right, just to be safe. And suddenly, your stomach just drops. You see these terrifying numbers flashing in bright red font. Voltages are dropping. Temperatures are seemingly spiking into the danger zone.
And your immediate visceral reaction is just panic. Pure panic.
Exactly. You think, my power supply is actively dying right now. It's going to send a power surge through the motherboard and fry my entire system.
And before you know it, you are opening a new tab, logging into some electronics retailer, and panic buying a brand new, wildly expensive power supply that you absolutely did not need.
Which means tossing a perfectly functional, heavy-duty piece of electronics packed with perfectly healthy capacitors, copper wiring, and transformers straight into the e-waste bin.
It's tragic. This exact scenario plays out thousands of times a day, all around the world. It's a literal epidemic of premature hardware disposal, and it's driven entirely by software panic.
Well, today, we are going to try and save your budget.
Yes, we are.
We're going to rescue your aging hardware from that e-waste bin and show you how to see right through these digital illusions. But to do that, we have to start at the physical foundation.
Right, the setup.
What exact state is the hardware in? We need to understand the actual victim sitting on the test bench in the source material. We need to know what piece of silicon we are torturing and the exact brutal conditions of the stress test they set up.
Well, the subject of this experiment is a really fascinating choice. It is a true veteran of the computing world, the AMD FX 8300 processor.
The FX 8300, okay.
Now, the word veteran here is absolutely absolutely crucial context. We are not talking about a brand new, ultra-efficient 5-nanometer piece of silicon fresh off a modern assembly line.
No, definitely not.
The FX series, which was based on the infamous pile driver microarchitecture, for anyone keeping track, is older, heavier equipment. From an engineering standpoint, it is notoriously power-hungry and runs quite hot compared to modern standards.
Wait, let me stop you right there. If they are trying to prove a point about power supplies being reliable, why pick a notoriously power-hungry, inefficient processor from several generations ago? I mean, wouldn't you want to test something new?
What's fascinating here is the logic behind the selection. When you want to truly test the limits of a power delivery system, you need a worst-case scenario.
Oh, I see.
Yeah, because modern processors are incredibly good at sipping power. They use aggressive downclocking in these tiny micro-sleep states to save energy.
They're super efficient.
Right. But the older FX series does not have those modern refinements to the same degree at all. It demands massive, constant amounts of current to feed its cores.
So it's basically a power hog.
Exactly.
Yeah.
When you put veteran equipment to the test like this, the reliability of every single component, especially the power supply delivering the electricity, becomes hypercritical.
That makes sense.
If an older system's power supply has genuinely degraded over the years, a heavy, sustained stress test on a power-hungry chip like the FX8300 will absolutely catastrophically expose that weakness.
Okay, that makes perfect sense. It's the ultimate trial by fire. You don't test a bridge by driving a bicycle over it, right? You test it by driving a convoy of lead-filled trucks over it.
Perfect analogy.
So the researchers set up this veteran processor and ran it through two very distinct states to compare exactly how the electrical system behaves under different loads.
Let's break those states down.
Yeah, let's look at state one.
All right.
The source describes this as pure stock. There is no tinkering in the BIOS, no pushing the voltage limits. The processor is just running at its factory base clock speed of 3.3 gigahertz, and it's put under a dedicated FPU load.
Right, an FPU load.
Let's translate that for anyone who isn't, spending their weekends reading CPU architecture white papers. What is an FPU load actually doing to the physical chip?
Well, FPU stands for floating point unit.
Hmm.
To visualize this, you have to think about what a processor actually does at a microscopic level.
Okay, zooming in.
It's essentially millions of microscopic switches doing math. Some math is simple, like adding whole numbers, but the floating point unit is the specific dedicated section of the processor core that handles incredibly complex mathematical operations involving decimals.
Decimals? Like what?
Think of calculating the precise trajectory of light rays in a high-end video game engine, or executing the dense physics calculations required to render a 3D animation.
So it's like the heavy lifting math department of the chip.
Exactly. When you run a synthetic FPU stress test, you are sending an unrelenting, unbroken wave of these complex calculations directly to that specific part of the processor.
Just hammering it.
You are forcing the silicon to work as hard as physically possible, nonstop, without any breaks. This draws a significant, steady, and massive amount of electrical current from the power supply.
And it's called synthetic because of how unnatural it is, right?
Yes, it's a synthetic load because it pushes the CPU far harder and more consistently than almost any normal daily task like browsing the web or even playing most games ever would.
So state one is already brutal, the chip is sweating, but then they flip the switch to state two. And this is where the researchers get truly aggressive.
This is where it gets fun.
They apply what they call a mild overclock, pushing the CPU's core frequency from 3.3 gigahertz up to 3.6 gigahertz. That's a solid 9% bump in raw clock speed.
Insignificant for that chip.
No, not at all. But they didn't just stop at the processor. In state two, they are simultaneously stressing both the CPU and the GPU, the graphics card, at the exact same time.
A dual torture test.
Yeah. Now, we need a mechanism-based analogy here to understand why this matters. I want to talk about voltage and current for a second. When you overclock and stress the GPU at the same time, it's not just making the computer work harder. It's like a plumbing system, right?
That is the perfect way to visualize it. Think of your power supply as the main water pump for your entire house.
Right.
The voltage is the actual water pressure in the pipes. The current, which we measure in amps, is the sheer volume of water flowing through those pipes.
Right. So when the PC is just idling on the desktop, it's like having a single bathroom sink turned on at a slow drip. The water pressure, the voltage, is incredibly high and stable because almost no water is flowing.
Exactly.
But when they trigger state two, overclocking that power-hungry FX processor while simultaneously maxing out the graphics card. It's like someone suddenly ran through the house and turned on every single faucet, every shower, the dishwasher, and the lawn sprinklers, all to maximum flow at the exact same millisecond.
Yes, you are demanding maximum continuous current draw. The
Yeah.
graphics card is usually the single most power-hungry component in any modern computer.
By far.
So by stressing it alongside an overclocked veteran CPU, you are creating an absolute worst-case scenario for the power supply's internal components. You are pulling massive amounts of wattage across multiple electrical pathways all at once.
So what happens if the power supply isn't up to it?
If the power supply has any degraded capacitors inside it, those are the parts that are supposed to smooth out the electrical flow, or if its voltage regulators are failing, the water pressure in our analogy is going to completely collapse.
The voltage will just drop.
Right, and the system will crash.
Yeah.
It's the perfect environment to see if this older veteran hardware is still robust enough to handle extreme demand, or if it really is ready for the scrap heap.
Man, I am practically sweating just thinking about my own PC enduring that. So the stress test is running. The veteran FX8300 is drawing massive current. The GPU cooling fans are absolutely
The
roaring.
room's probably getting warm.
Oh, for sure. Now we turn our eyes away from the physical box and look at the screen. We look at what the system thinks is happening according to the software dashboard versus what is actually happening in physical reality.
And this is where the source material drops the bomb.
Yeah.
The ultimate false alarm.
During this massive system-wide stress test, the researchers pull up AIDA64. Now, for a little context, AIDA64 isn't just some obscure shareware program. It is one of the most popular, widely respected, and heavily utilized system diagnostic and monitoring software tools on the planet.
Oh yeah, everybody uses it.
Professional overclockers use it, tech reviewers use it, people trust it implicitly. But as they look at the voltage readings updating on the screen, AIDA64 starts showing a terrifying metric. It's looking specifically at the 3.3 volt rail, and it shows the voltage actively plummeting.
Just dropping like a stone.
It drops down from 3.3 down to 3.1, and then it hits exactly 3,000 volts in bright, flashing red text.
Wow. Okay, to truly understand the gravity of that specific number, 3,000 volts, we need to talk about how electricity is divided up inside a computer.
Please do, because 3.0 doesn't sound that far from 3.3 to a layman.
Well, a power supply doesn't just shoot a single stream of electricity into the motherboard. It splits the power from your wall into different voltages called rails.
Okay.
The 12-volt rail is the heavy lifter. It powers the massive, power-hungry components like the CPU and the graphics card. The 5-volt rail handles secondary devices like USB ports and older SATA hard drives.
Okay, so where does the 3.3 volt rail fit into this ecosystem? Why is it so crucial?
The 3.3-volt rail is the delicate, highly sensitive pathway. It doesn't power the big muscles. It powers the central nervous system.
Oh, wow.
Yeah, it provides electricity to the motherboard's core logic, the chipset, the incredibly fast M.2 NVMe solid-state drives, and the system memory logic.
So the brains of the operation.
Exactly. These are the components that govern the fundamental communication and data transfer of the entire computer. And they operate on incredibly tight, microscopic electrical tolerances.
So what actually happens inside the chips if that voltage drops too low? I mean, I understand the screen turns red, but physically, why is 3,000 volts a disaster for system stability?
It comes down to how digital logic gates work. At the deepest microscopic level, a computer only understands ones and zeros.
Right, binary.
But physically, there is no such thing as a 1 or a 0 inside a wire. There's only electricity. So engineers set specific voltage thresholds to define those numbers.
How does that work?
For example, on a 3.3-volt system, the hardware might be designed so that any electrical pulse measuring above 2.8 volts is registered by the chip as a 1. Anything below 0.8 volts is registered as a 0.
Oh, I see where this is going. The space between those numbers is the danger zone.
Precisely. If the power supply suddenly fails to maintain the pressure, and the 3.3V rail drops to a flat 3.V as the software claims, the entire electrical baseline shifts downward.
The pressure is gone.
The pulses that are supposed to be ones start getting weaker and weaker. Eventually, the signal gets so squished and distorted that the memory controller or the chipset just gets confused.
It can't tell the difference anymore.
Exactly. It reads a 1 as a 0. It corrupts the data packet. The chipset loses communication with the storage drive because it literally can't understand the electrical whispers anymore.
So if that 3.00V reading on the AIDA64 screen were actually real, The system wouldn't just slow down. It would be a catastrophic failure of basic logic.
A complete collapse.
The computer would instantly suffer a blue screen of death, or the motherboard would trigger a hard, immediate power cut to protect itself from data corruption. There is no middle ground, is there?
No.
At 340V, a working PC stops being a working PC. It becomes an inert brick of silicon.
Yes. But, and here is the massive, glowing contradiction that the source material points out with so much eagerness, despite the AIDA64 software screaming in red text that the system is dying, despite the digital numbers saying the computer's logic gate should have collapsed 5 minutes ago. The veteran FX chip just keeps right on crunching numbers.
It's totally fine.
The heavy FPU stress test keeps running flawlessly. The GPU keeps rendering. There isn't a single stutter, no screen tearing, no blue screen, no sudden reboots.
That is wild.
The physical mechanical system is behaving absolutely perfectly, while the digital software is screaming that the house is on fire.
Hold on, this is the part that drives me crazy. If that 3.0V reading isn't real, if it's completely fabricated by the system, why does the motherboard manufacturer even bother including the sensor?
It's a fair question.
I mean, if it's that inaccurate, aren't they just opening themselves up to endless customer support tickets from terrified users? Why would this highly respected software lie to us?
That is the perfect question. And it takes us into the physical mechanism of how a computer actually feels itself. You have to remember, software like AIDA64 is just code. It doesn't magically know the voltage in the physical world.
Right, it needs hardware to tell it.
It has to rely on a physical interpreter. On almost every consumer motherboard, there is a tiny, incredibly cheap, mass-produced silicon square called a Super I/O chip, often made by companies like Nuvoton or ITE.
Okay, a Super I/O chip.
And inside that tiny chip is an ADC, an analog-to-digital converter.
Okay, an analog-to-digital converter. Break down the actual physics of what that chip is trying to do for us.
Well, think about the electricity flowing from the power supply. That is analog. It is a continuous physical wave of electrical pressure moving through a copper trace on the motherboard.
A real physical wave.
But software can only read digital numbers, discrete bits of data. So the job of the ADC is to take thousands of tiny snapshots of that analog electrical wave every second, measure the height of the wave, and translate that physical measurement into a digital number that the software can print on your screen.
It's like taking a continuous, smooth vinyl record and trying to chop it up into an MP3 file. You have to sample it over and over.
Exactly. That's a great way to put it. But here is the critical flaw. These Super I/O chips are not scientific-grade lab equipment.
Not at all.
They are $2 chips designed to be as cheap as possible. And they're subject to massive amounts of electrical noise.
Electrical noise? You mean like static on a radio? How does that happen inside a computer case?
It's all about electromagnetic interference, or EMI. Think about the environment inside a PC case during a heavy stress test, like State 2 in our experiment.
Lots of power moving around.
Right. Right next to that cheap Super I/O chip, you have the CPU. And to feed the CPU, the motherboard uses components called VRMs, or voltage regulator modules.
Okay, VRMs.
These VRMs are essentially microscopic dams that step down the 12 volts from the wall into the tiny 1.2 volts the processor actually needs. To do this, they switch on and off hundreds of thousands of times every single second.
That sounds violently chaotic at a microscopic level.
It is. It's incredibly violent electrically. And physics dictates that whenever you have massive amounts of electrical current rapidly switching on and off, you generate expanding and collapsing magnetic fields.
Oh, I see.
These invisible magnetic fields pulse outward from the VRMs and literally wash over the entire motherboard. When those magnetic fields hit the tiny, delicate copper traces leading to our cheap Super I/O chip, they physically induce rogue microvoltages inside the wire.
Wait, really? The magnetic field is creating new electricity in the wire?
Yes. It physically alters the analog signal before it even reaches the sensor.
Oh, wow. So the sensor isn't necessarily broken. The actual physical wave of electricity being fed into the sensor is being warped and distorted by the magnetic storms happening an inch away.
Exactly.
The ADC samples a trough of the wave that was artificially deepened by magnetic interference, does the math, and spits out 3,000 volts. So the software is faithfully reporting a 3.0 VOV drop, not because the actual power supply is failing, but because the cheap sensor reporting the data is being completely overwhelmed by the electromagnetic noise of the system.
Precisely. You are seeing the measurement of interference, not the measurement of the power supply.
And the psychological impact of seeing those failing numbers on a screen is just profound. We are deeply conditioned to trust digital dashboards.
We really are.
If the check engine light comes on in your car, you immediately pull over. If your bank app says you have $0, your heart skips a beat.
Naturally.
So when a PC builder, especially someone newer to the hobby who has poured their savings into a machine, opens their software and sees 3.000 flashing in bright red, the immediate psychological reaction is pure fear.
Absolute panic.
They don't think about analog to digital converter quantization errors. They don't think about electromagnetic interference from voltage regulator modules. They think, my rig is dying and it's my fault.
And as the source material points out,
Yeah.
that engineered fear directly leads to the premature discarding of perfectly good hardware. They log onto an online store, spend $150 on a new power supply, spend hours ripping out all the meticulously routed cables of the old one, and throw it in the trash.
Just throw it away.
All because a $2 mass-produced sensor got a little dizzy from magnetic noise. It is a phenomenal waste of money, and it contributes massively to the global e-waste crisis.
So since we can't trust the motherboard's digital interpretation of the electricity, how do we actually intercept the raw current before the computer's logic gets a hold of it? The host of our source material experiment decides to bypass the digital illusions entirely, which I love.
It's the only way to be sure.
We need the actual truth. We need to measure the physical reality of the electricity flowing through these wires. And that leads us to the introduction of a completely different kind of diagnostic tool.
The heavy artillery. The professional digital multimeter.
Right. They bring out a professional Unity digital multimeter. Now, for anyone listening who might be a novice or who has never tinkered at the raw component level, let's visualize this.
Sure, let's paint a picture.
A multimeter is a physical handheld diagnostic tool. It looks a bit like a bulky walkie-talkie with a big dial on the front and a digital screen. It has two thick wires coming out of it that end in sharp metal probes, a red one and a black one.
Very intimidating if you haven't used one.
Yeah, but unlike the motherboard sensor, it doesn't rely on complex analog to digital translations filtered through noisy silicon. It measures the raw physical properties of electricity: voltage, current, and resistance.
It works by introducing an incredibly high internal resistance between its two probes. When you touch the probes to a circuit, it measures the pressure of the electrons trying to push through that resistance. It is an unvarnished, direct measurement of physics.
But wait, I'm looking at my own rig right now in my head, and the idea of poking sharp metal sticks into a live 24-pin connector while the PC is actively running a heavy stress test sounds like a fantastic way to cause a massive short circuit and permanently fry my motherboard.
It definitely can be if you're careless.
Is there a trick to doing this safely? Let's give the listener the true beginner's guide to this physical hardware diagnostic. How did the source safely extract the truth? Because I want to know how diagnostics like this can actually save the user's budget from unnecessary purchases.
Safety and proper procedure are absolutely paramount here. We have to stress that. The diagnostic methodology laid out in the source involves reading the voltage directly from the 24-pin ATX connector.
Okay, the big cable.
Right. To visualize this, look inside any desktop PC. There is a massive, thick bundle of multicolored wires that runs from the power supply box and plugs into a large plastic rectangle on the right side of the motherboard.
Usually right next to the RAM.
Exactly.
Yeah.
That is the 24-pin ATX connector. It is the main highway providing power for the entire system. Now, to measure this safely and accurately, you perform a technique known in electrical engineering as back probing.
Back probing. Okay, walk me through the physical sensation of back probing. How exactly do you do it without causing a disaster?
Well, first and foremost, you clear your workspace. Ensure you are grounded, touch a metal cable leg, or wear an anti-static wristband so you don't introduce static electricity from your body into the sensitive motherboard.
Good tip.
You turn on your multimeter and set the main dial to read DC voltage direct current, because that is the type of electricity a PC uses. Usually you'll set it to a range that can comfortably read up to 20 volts.
Okay, dial is set.
Now look at that 24-pin ATX connector while it is firmly plugged into the motherboard. You do not unplug it.
Wait, leave it plugged in?
Yes. The system must be actively running the stress test under heavy load to get an accurate reading of how the power supply behaves under pressure.
Right, because if you unplug it, the motherboard loses power, the system shuts off, and you're measuring a dead wire with 0 voltage. That makes sense.
Precisely. Now, ATX power supplies follow a very strict, universal color-coded standard. The 3.3-volt wires, ones we are so interested in today, are universally coated in orange plastic.
Orange for 3.3 volts.
And the ground wires, which complete the electrical circuit, are universally black. So to measure the 3.3V rail, You take the black probe of your multimeter, or the negative probe. You do not touch the motherboard itself.
Keep the probes away from the board.
Instead, you look at the top of the plastic ATX connector where the wires go in. You carefully slide the sharp metal tip of the black probe down into the back of the plastic connector housing, right alongside one of the black ground wires.
Oh, I see.
You slide it down until you feel the tip make physical contact with the tiny metal crimp hidden inside the plastic.
So you are basically slipping the needle past the plastic sheath to touch the bare metal terminal inside the plug.
Yes. And then you take a red probe, the positive probe, and you carefully slide it down alongside an orange wire, making contact with its internal metal trim.
Wow, okay.
Now here is the critical safety warning.
Yes.
You have to be incredibly steady. You cannot let the two bare metal probes touch each other while they're in the connector, and you cannot let a probe slip and touch a neighboring pin.
What happens if you do?
If you bridge the orange 3.3V wire with, say, a red 5V wire, you will create an immediate short circuit. You will hear a pop, you will smell magic smoke, and you will have permanently destroyed your motherboard.
Magic smoke is never a good sign. It sounds like a delicate surgical procedure. But the logic is incredibly sound. By doing this back probing, you are effectively tapping directly into the raw electrical stream flowing straight out of the power supply, right before it ever hits the noisy, magnetically chaotic environment of the motherboard.
Exactly. It is a direct physical connection. This physical tool is completely immune to the electromagnetic noise of the CPU VRMs, and it completely bypasses the poor quality of the motherboard's analog-to-digital converter.
It's just raw physics.
It is the unvarnished truth of the hardware, and it's how a $20 tool saves you from a $150 mistake.
Okay, so the probes are securely in place, the system is running, the multimeter screen is active. On computer monitor, the AIDA64 software is screaming that the voltage is at a catastrophic, system-killing 3.9 volts.
The tension in the lab is high.
And then the moment of truth. What does the physical hardware tool actually say? Let's look at the real numbers pulled straight from the copper wire. Under state 1, pure stock running at 3.3 gigahertz, the physical multimeter reads 3.25 volts.
Interesting.
And then they ramp it up to state 2. The 9% overclock is applied, the GPU fans are roaring, the system is drawing maximum continuous current, the multimeter reading drops slightly, settling at 3.17 volts.
Now, let's critically analyze those specific physical readings, because this is where the panic usually sets in for consumers who don't understand the underlying electrical engineering.
Right, because 3.17 isn't 3.3.
Exactly. A builder sees 3.17V on their multimeter and thinks, well, the box says 3.3 volt, and 3.17 is not 3.3, so my power supply must be failing.
I mean, I would probably think that too.
But that is fundamentally not how power delivery or physics works. We have to introduce the concept of the hardware minimum and electrical tolerances.
Wait, electricity isn't perfect, so there has to be some wiggle room built into the system, right?
Yeah.
What is the actual bottom line limit before it's officially considered failing?
To understand the limit, we have to look at the rulebook. In 1995, Intel introduced the ATX specification.
1995, wow.
Yeah. Before that, computer power supplies were basically the Wild West. Every manufacturer did whatever they wanted, and compatibility was just a nightmare. The ATX standard is a massive, strictly enforced engineering document that every power supply manufacturer on Earth has to follow if they want their unit to work in a PC.
It's the law of the land.
It is. And the engineers who wrote that standard knew about Ohm's law. They knew that copper wires have intrinsic physical resistance, and as you pull more current through a wire, the voltage naturally drops.
Right, the pressure drops as the flow increases.
So the ATX specification dictates that the 3.3 volt rail must stay within a strict 5% tolerance window under absolutely any load. It is legally allowed to fluctuate as long as it stays within that specific 5% margin.
Okay, let's crunch the numbers on that tolerance. What is the absolute floor?
If we calculate a 5% variance on 3.3 volts, that gives us a margin of 0.165 volts. If we subtract that from the target 3.3 volts, we get the absolute minimum allowable voltage, the ATX legal floor.
And that is?
That number is 3.135 volts.
3.135 volts. So as long as the power supply is delivering anything above that specific number, it is operating 100% perfectly within specification, even under the most brutal load.
Exactly. 3.135 volts is the hardware minimum. During the absolute maximum overclocked stress test in state 2, the physical multimeter measured the raw copper wire at 3.17 volt.
Which is higher.
That is significantly above the 3.135 V minimum floor. Yes, there is a slight voltage droop, which again is entirely natural when you pull massive current through copper wire due to resistance, but it is perfectly healthy. It is operating exactly as designed.
So what does this all mean for the veteran equipment on the test bench?
It means there is absolutely no PSU degradation whatsoever. The veteran power supply, despite its age and the massive thermal load of the FX processor, is acting exactly as a brand new, ultra-premium power supply would.
It's a tank.
It is handling the immense chaotic load beautifully. The terrifying 3.00 V reading flashing in red on the computer screen was nothing more than a massive, egregious margin of error from cheap software sensors overwhelmed by magnetic noise.
Wow.
The real hardware measurements prove, without a shadow of a doubt, that the power supply is perfectly healthy.
The software lied. It's incredible. The digital dashboard was off by a massive 0.17 volts compared to reality. In the world of delicate microelectronics, a 0.17 volt delta is literally the difference between life and death for the logic gates.
It's huge.
That $20 handheld multimeter just saved a $150 power supply from being chucked into the garbage bin. But what's fascinating is that our source material doesn't just stop at the power supply.
No, they keep going.
Having definitively proven the power delivery is stable and the software is hallucinating, the researchers pivot. They want to look at the secondary physical effects of this extreme overclocking experiment. They want to see if the rest of this veteran system is actually holding up to the punishment.
Because stable power delivery is really only half the battle of system stability. When you push electricity through silicon, it doesn't just do math.
Right.
Due to electrical resistance within the microscopic transistors, a large portion of that electrical energy is inevitably converted into thermal energy heat.
And heat is the enemy.
Exactly. If you increase the clock speed and you increase the current to support that speed, you are drastically increasing the thermal output of the processor. If you can't shed that heat, the processor will literally cook itself to death.
Right. So let's look at the physical consequences of that 9% clock speed bump. We went from 3.3 gigahertz to 3.6 gigahertz. We know the power supply handled the extra current demand. But what about the cooling system?
The mechanical side.
Specifically, the cooling fan sitting on top of that massive heatsink attached to the veteran FX8300 processor. How did the mechanical cooling system react to the sudden influx of heat?
Well, the physical reaction of the system was immediate and entirely measurable. Modern motherboards have built-in thermal probes, which, unlike voltage sensors, are generally quite accurate because they rely on simple thermistors.
Okay.
As the silicon started to heat up from the overclock, the motherboard automatically commanded the cooler fan to spin faster to compensate. The source material meticulously recorded the fan speed ramping up. It went from a baseline of 2,070 RPM revolutions per minute up to 2,327 RPM.
So the fan spun up by about 250 RPM. It's aggressively pushing a higher volume of ambient air through the aluminum fins of the heatsink to wick away that extra thermal energy.
Working exactly as intended.
But here's the most surprising part to me, and I need you to explain the physics of this. We are talking about an older, highly power-hungry, famously hot architecture. You would expect the temperatures to just absolutely skyrocket when you overclock it and apply a heavy FPU load.
You really would.
But the thermal result revealed in the test is astounding. Despite the heavier load, despite the 9% overclock, the core temperatures only climbed by 5 degrees Celsius. The CPU settled and sat incredibly comfortably at a highly safe 58 degrees Celsius. How is that physically possible?
To understand why that is so remarkable, we have to look at the thermal dynamics of silicon. Most modern processors, if you apply a heavy synthetic FPU load, will happily boost their clock speeds until they hit a thermal wall, usually around 90 or even 95 degrees Celsius.
That's boiling water.
Right. At that point, they start thermal throttling, which means they intentionally rapidly slow their own clock speeds down to prevent the silicon from physically melting or degrading.
Okay.
So sitting at a mere 58 degrees Celsius under a heavy synthetic load means this older processor has massive thermal headroom. It's not even close to the danger zone.
Let me try a metaphor here to make sure I grasp this. When you overclock and stress the CPU, it's not just working harder, it's generating internal friction, right?
Basically, yes.
Yeah. It makes me think of an engine. It's like we took an older V8 engine that was cruising on the highway, and we suddenly commanded it to start towing a heavy trailer up a steep hill.
Good visual.
The engine's RPMs, a cooling fan on our PC, went up slightly to compensate for the massive effort, but the engine block's core temperature barely shifted at all. The radiator handled the extra heat effortlessly. The engine is not overheating, it's practically not even breaking a sweat. Is this typical for older veteran hardware to hold up this remarkably well under stress? We are always told old tech runs incredibly hot.
If we connect this to the bigger picture of hardware longevity,
Hmm.
it is a powerful revelation. It speaks volumes about the quality of the specific physical cooling solution used in the test, yes. But more importantly, it definitively proves that the underlying silicon of these older chips is incredibly robust.
It's really built to last.
It is rock solid. We have this pervasive industry-driven perception that tech ages like milk, that after 5 or 6 years, the silicon itself becomes brittle, unstable, and dangerously hot.
Yeah, that it just gets tired.
Exactly. But silicon doesn't degrade in the way organic material does, unless you pump dangerously high voltage through it for years on end, a process called electromigration, where electrons literally push metal atoms out of place. A processor from 10 years ago is fundamentally the exact same physical, capable object it was the day it left the cleanroom factory.
Wow.
This test proves the mechanical cooler is easily handling the thermal load, and the veteran silicon is far more capable than the panic-inducing software dashboard implies.
And that realization that old hardware is still incredibly physically capable leads us perfectly into the deepest, most controversial part of today's deep dive.
There we go.
With the physical experiment concluded and the veteran hardware proven utterly victorious over the software's digital lies, we have to zoom out. We have to look at the broader implications for the global tech industry, for the consumer market, and most importantly, for you, the listener.
Because there's a big gap here.
Huge. There is a massive gaping discrepancy between what this physical test just proved with a voltmeter and what the tech industry tells us every single day through targeted ads.
We are firmly entering the territory of what critics call the upgrade illusion.
Exactly, the upgrade illusion. Modern tech marketing isn't just about showing off new features. It is a multi-billion-dollar psychological juggernaut. It is a machine meticulously designed with one single purpose: to make you feel inadequate.
And they are very good at it.
They really are. Aggressive advertising campaigns work tirelessly across YouTube sponsorships, social media influencers, and tech blogs to convince you that your older rig, the one running that perfectly fine FX 8300 or maybe a GTX 1080 graphics card, is an archaic potato.
Yeah.
They weaponize terms like bottlenecking, outdated architecture, and obsolescence. They want you to believe that if you aren't upgrading your motherboard and power supply every single digital season, you are missing out on performance. Your system is secretly failing in the background, and you are falling irredeemably behind the curve.
And this specific source material provides a deeply powerful, data-driven counter-narrative to that marketing barrage.
It totally shuts it down.
It empirically shows that an older system, when measured with objective physical reality rather than software estimates, is not only stable, but entirely capable of handling significant synthetic stress without a single physical failure.
Right.
Which begs a deeply philosophical and analytical discussion about the industry. Why does the software, which is very often bundled directly by the motherboard manufacturers themselves, or heavily promoted within the broader tech ecosystem, so frequently tell us our systems are failing when they aren't?
Right. This is the million-dollar question. Are these wildly inaccurate software sensor readings just a happy accident for the hardware industry, or is there something more systemic going on here?
The source text raises the specter of planned obsolescence. Now, planned obsolescence is a well-documented historical industrial strategy where products are artificially designed with a limited useful life, either physically breaking down or becoming perceived as obsolete, so the consumers are forced to replace them repeatedly.
Like light bulbs burning out on purpose.
Exactly like that. In the context of our deep dive into the 3.3V myth, the question is nuanced. Is the industry's reliance on cheap, easily confused super I/O chips an intentional malicious strategy?
Are they doing it on purpose?
Do massive hardware manufacturers know these analog-to-digital converters will eventually drift due to magnetic noise and show scary, inaccurate numbers, thereby inducing a software panic that directly drives the highly profitable sales of new motherboards and replacement power supplies?
Or is it simply a matter of massive corporate incompetence? I mean, is it just a mundane cost-cutting measure where some accountant in a boardroom decided that spending an extra 50 cents per motherboard on a magnetically shielded lab-grade voltage sensor simply wasn't worth the hit to their profit margins?
It's the classic debate of malice versus incompetence, really. If you deliberately put a $2 unshielded sensor right next to a massive magnetically noisy VRM module, you are guaranteed to get bad data eventually.
It's just physics.
Exactly. Whether corporate engineers do that on purpose to subtly manipulate us into buying new parts, or they just do it to save $2 on a mass-produced assembly line. The end psychological and financial result for the consumer is exactly the same. Pure panic and wasted money.
But I want to be super clear here, though. Let's naturalize the vital disclaimer that the source material goes out of its way to establish.
Yes, very important.
We aren't pointing fingers at specific executives, and we aren't saying the developers of AIDA64 or the engineers at major motherboard manufacturers are sitting in a dark room running some malicious global conspiracy to steal your money.
No, we aren't saying that at all.
This deep dive is fundamentally an observation of physical hardware limitations. Cheap sensors are just cheap sensors, and software can only be as accurate as the flawed hardware feeding it data. We're just giving you the tools to double-check their homework before you open your wallet. The goal is to educate the user to recognize those physical limitations, not to start a witch hunt against tech companies.
That is a crucial distinction. The overarching theme of this entire analysis is about shielding the consumer through education. True, hardware-level diagnostics, like taking an afternoon to learn how to use a $20 digital multimeter, are the ultimate impenetrable shield against this relentless marketing barrage.
Knowledge is power.
It really is. When a user fundamentally understands the physics of their own machine, they can't be bullied by a flashing red light on a software dashboard. They know that a 3.17V reading under massive load is actually a triumph of electrical engineering, not a reason to pull out their credit card.
It completely reframes the power dynamic between the everyday user and the multi-billion-dollar corporation. Diagnosing it yourself physically saves your personal budget from entirely unnecessary purchases. It stops perfectly good veteran hardware from ending up in a toxic landfill. It's incredibly empowering. You are taking back control of reality from the software illusion.
And that brings us to the ultimate foundational lesson of today's deep dive in the solder, silicon, and voltmeter lab.
The big takeaway.
If there is only one technical principle you take away from this extensive journey into PC hardware, it is this: never ever base your hardware upgrade or repair strategy solely on digital software monitoring.
Say it louder.
As the indisputable physical reality of the multimeter proved beyond a shadow of a doubt today, true system stability is proven by a physical tool in your hands, measuring raw voltage, not by flashing pixels on a digital screen.
The physical world will always supersede the digital approximation of it. When in doubt, measure the reality.
Which raises an important, deeply unsettling question to leave you with.
Oh boy.
Well, think about it. We've just spent this time seeing exactly how a multi-thousand-dollar PC ecosystem can be completely undermined and perfectly good hardware thrown away, all because a cheap, magnetically noisy sensor caused a software panic.
Right.
If the software sensors for our PC's voltage can be off by such a massive panic-inducing margin, what other digital metrics in our daily lives are we blindly trusting without question?
Oh man, that's a scary thought.
Think about your smartphone. When the operating system suddenly tells you your battery health is degraded to 79% and heavily suggests you need to buy an expensive new phone, is that physical reality? Or just another software illusion driven by a cheap sensor?
I've literally upgraded my phone because of that exact notification.
What about your highly computerized smart car's digital dashboard suddenly flashing a warning that it's time for an incredibly expensive dealer service? Are we blindly trusting these digital dashboards to tell us it's time to buy something new without ever once checking the physical reality for ourselves?
That is a profoundly unsettling yet incredibly important thought to carry with you next time any digital screen flashes a warning at you. Remember the patient in the hospital room with the flatlining monitor, but a perfect pulse. Look at the reality, not just the readout.
Always check the pulse.
Exactly.
Yeah.
If this deep dive just saved your wallet, or if it made you look at that aging veteran rig sitting on your desk with just a bit more respect for the robust silicon inside it, you need to hit that subscribe button right now. Drop a like on this episode and leave a comment down below with a suggestion for what dense technical topic or hardware myth we should explore and bust next. Share this with your tech buddies or anyone in the PC building niche who desperately needs to hear the truth about hardware diagnostics and the upgrade illusion.
Spread the word.
I promise you, there will absolutely be more content, more deep dives, and more technical myth busting on this specific topic in the future. Thank you so much for your attention, for taking the time to learn the physics with us, and as always, join us next time as we take another deep dive. And as the original creator of our video source material always says, don't let the software fool you. See you in the next video.